Some harder problems now with induction. So this one, we want to prove that x plus y to the power of n is greater than x to the power of n plus y to the power of n. So like some of the expansion here will be greater than that. Now that should be obvious, but let's prove it there. So show true for n is greater than 1, so we put n is equal to 1 into both. So x plus y is equal to x plus y, so it's true for when n is equal to 1. Assume it's true for n is equal to k then, so x plus y to the power of k is greater than x plus x power of k plus y to the power of k. We are going to be required to prove that x plus y to the power of k plus 1 is greater than x to the power of k plus 1, y to the power of k plus 1. So we start with our left hand side again. X plus y to the power of k plus 1. That would be equal to, again we're using our indice laws, x plus y to the power of 1 times x plus y to the power of k. Now we know that x plus y to the power of k is greater than or equal to x to the power of k plus y to the power of k. Then we're going to expand that out, get x to the power of k plus 1, x times y to the power of k, y times x to the power of k, and y to the power of k plus 1. Let's rearrange it. So there's what we wanted to prove, but we got this extra part added on, so we know all this would be greater than x to the power of k plus 1 plus y to the power of k plus 1, which was, what we started off with, is greater than what we finished with. So that's proved. So number 2, x to the power of n minus 1 divisible by x to the power of 1, and x minus 1. So if we show true again for n is equal to 1, so x to the power of 1 minus 1 over x to the power of 1, x minus 1 gives us 1. That's true. That's divisible. Assume it's true for n is equal to k, so we do our assumption step again. X to the power of k minus 1 divided by x minus 1 is equal to m, or x to the power of k minus 1 would equal to m outside of x minus 1. And then we add the 1 on both sides, we get an expression for x to the power of k. Now again, you could have done this in step 3. I've elected to do it in step 2, and then I'm going to try and substitute that. So again, I want to prove that's true for n is equal to k plus 1. So I'll start with x to the power of k plus 1 minus 1. So x outside of x to the power of k. So again, I can make my assumption step and substitute it in. mx minus 1 plus 1. Starting to clean up what's inside the bracket gives me x power mx minus m plus 1. Subtract, add, expand, gives us m times x squared. We get a minus m plus 1 lot of x, and then minus 1. Which, if I look at that, I can start to factorise that and get mx plus 1 and x minus 1, which obviously would be divisible by x minus 1. So if you wanted to have a look at that, I've just broken it up into that part there to give us that expansion there. So you can see the collecting of terms there. So if you want to expand that, minus mx and plus x with the minus 1, and we've just got a case where we can't factorise, so we'll group them in pairs and then be able to factorise there. So there's that proof. That's a little bit harder. That's starting to work on a few different concepts and a lot more work with algebra. So again, we've got to get our algebra settled and be really good at it to make sure we're able to prove some of those steps in the step 3 of the induction process.